Hello, everyone. Welcome. So today, my name is Shayan Gharan. I'm from University of Washington, and today I will tell you about the Markov chain Monte Carlo method and its application and the math behind it. The stuff I'll talk about are based on joint works with my student Kwikwi Leo and my collaborators Nima Anani and Cynthia Winzan. Okay, so let me get started. Let me tell you the context that this talk is about. So let's say you have a ground set of elements n, and you assign a weight function, a non-negative weight function, to subsets of 2 to the n. The question is that you want to generate a random sample with probability proportional to these weights, meaning that the probability of S, you want to be the weight of S over the summation of weight of all of the sets. Okay, so another related problem is to estimate the summation of weights of all of the sets. So the difficulty of this problem is that you can have exponentially many sets in the support of W, exponentially in N, and you want to be able to do these tasks efficiently in polynomial time with respect to n. It turns out that these two tasks are closely related. In fact, if you can solve one, you can solve the other. If you can approximate one, you can approximate the other. I will not tell you about that in this talk. So what I'm going to focus in this talk is mainly on the sampling question, meaning that how can you generate a random sample from such a distribution? So before I begin to the math, I want to tell you some examples and applications of this. So let me start with some examples. Here are 4 examples. In the top left, you can see a machine called the card shuffler. And what it does is that it takes a deck of cards and sort of makes them random. It's used a lot in casinos to generate a random deck of cards. In the top right, you see the problem of generating a uniformly random spanning tree of a given graph. In the bottom left, you see the problem of generating a uniformly random independent set of a graph. And in the bottom right, we have the problem of estimating the permanent of a given n by n matrix. If you don't know what permanent is a sort of is the sum over all permutations. It's similar to determinant if you're familiar with determinant, except that you drop the sign. Now, these are some examples of type of quantities you want to sample or estimate. And these objects and several related ones have a lot of applications in all over the science. So I will not dig into the applications, but there are applications in optimization, statistical physics, systems, quantum, economics, and etc. Okay, so let me not tell you about that. So I just want to sort of end the intro of the talk with this nice motivating theorem for the talk. So this is a theorem I learned about when I was in grad school. It's by Bayer and Diaconis from 90s. They proved the following. Say you have a deck of cards like this one, and you want to make them random. Okay, so what can you do? There are a lot of ways to try to make it random. And a nice way you can do is this procedure called the riffle shuffle, where you divide this into 2 sides and sort of I mean, it's hard for me to perform under the camera, but you do something like what this guy is doing, that the host is doing in this picture. So this is this operation called the riffle shuffle. And what they proved is that if you do this operation about 3/2 log of n times plus maybe 1 or 2 more, then the deck will be almost uniformly at random. Okay. So this is a very interesting theorem. Percy Diaconis told me that after this, the name showed up at the headline of New York Times. He received a lot of calls from casino owners who wanted to sort of instruct their hosts or buy a machine to generate a random deck of cards. So just saying how applied this field could be, really. But okay, so now before I tell you about all of these, I need to first tell you about background material. So I'm going to start telling you about random walks and some theorems about them, and then I'll start talking about Markov chains and the Markov chain Monte Carlo method. So let me start by talking about a random walk. So let's say you have an undirected graph G. A simple random walk is basically a walker who starts at a vertex of this graph, and each time he goes to one of the neighbors uniformly at random. Okay. So this is a simple random walk on the unweighted graph G. If the graph is weighted, the walker will do the same thing, except that each time instead of going to a uniformly random neighbor, you go to an edge proportional to its weight, meaning the ratio of the weight of that edge to summation of the weights of all of the edges neighboring of that vertex. Now, one question you can ask is that how long does this take for this walker to visit all of the vertices in the graph? It turns out that for the worst case graph, it takes order of n cubed time. So meaning that whatever graph you give me with high probability after n cubed steps, you're going to visit all of the vertices. Why is that interesting? Here's a cool application. If you're given a pair of vertices S and T in a graph G, and you want to test whether S is connected to T, you can just run this random walker and wait for order of n cubed steps and see if if you hit T, if you visit T or not. And if you don't, then you know that with high probability they're not connected. Now you can think that this is very slow. You probably could have run the BFS or DFS algorithm to do that, but it turns out that this is a useful algorithm because it needs only log n bits of memory just to know that what is the ID of T and test whether you get to T or not. So it's a slow algorithm, but with very small memory. So this is a simple application of random walks, but we'll need more in this talk. So let's understand them more. So once you have a random walk, you can associate to it a matrix called the transition probability matrix. Here I've drawn the transition probability matrix of this cube graph that I have. So what is it? I have multiplied the adjacency matrix of this graph with 1/3. Why 1/3? Because the degree of every vertex here is 3. So for example, from 0, you're going to go to 1, 2, or 4 uniformly at random. So it's going to be 1/3, 1/3, 1/3 to go from 0 to 1 or 0 to 2 or 0 to 4. Okay. So here is a simple question you can think about. Let's say you start at 0. So at time 0, you're at 0. The question is, where will you be at time 1? If you think about it for a second, you see that you will either be at 1, 2, or 4 with uniform probability. Probably 1/3 you'll be at 1, 1/3 at 2, and 1/3 at 4. So in fact, the location at 1 is distributed according to the 0th row of this transition probability matrix P, like 1/3, 1/3, 1/3 at 1, 2, and 4. How about your location at x2? So you start from 1, so it would be equal probability at 1, 2, or 4. How about your location at time 2? So now you will be at with 1/3 at 1, 1/3 at 2, at 1/3 at 4. Where will you be in the next step? For example, you will be in 3 if you are in 1 or 2 and then come to 3. So you'll be in 3 probably 1/3 times 1/3 plus 1/3 times 1/3. So it's going to be 2/9. Probably to be at 3, 5, or 6 is 2/9. And then probably 1/3, you're going to come back to 0. So your distribution would look like this. And in fact, it is distributed according to the 0th row of the matrix P squared. Similarly, you can just follow this and see that at time t, your distribution of xt is the same as the 0th row of the matrix P to the t. Okay. So having that in mind, one thing you should have noticed is that if you start from 0, your distribution every time is changing. So what is the limit? The limit of this is what we are interested in, the stationary distribution. So we say pi is a stationary distribution. If when you are at pi in some step of the random walk, if your distribution is equal to pi in some step, in the next step it will also be equal to pi. So it doesn't change, and that's why it's called stationary. Now here is a fundamental theorem of this field, which says that if you have a graph G which is connected and it's not a bipartite graph, then for any vertex of V, if you start your random walk at V and you run it for long enough time, you're going to converge to the stationary distribution pi. And what is the stationary distribution? It is the distribution where you're at vertex V with probability proportional to its degree. So the pi of V is D of V over summation of the degree of all vertices, which is 2 times P, 2 times the number of edges. So, okay, so this is a cool theorem, but you can say, okay, the graph I was looking at so far, this cube graph is a bipartite graph. So what can I say? There is a trick to actually drop the non-bipartiteness assumption, which is to do a lazification. So what is this trick? The trick is that for every vertex of V, I'm going to add degree of V many self loops at V. And that would mean that, so something like this, here the degree is 3, I'm going to put 3 self loops at my vertices. And that means that when I'm at this vertex, with probably 1/2, I'm going to stay. I'm going to go through the self loop and stay. And probably 1/2, I would move according to the previous random walk. So in other words, what I'm doing is that I'm changing my transition probability matrix by averaging it out with the identity matrix, meaning that the probability 1/2, I move according to P, and the probability 1/2, I move according to the identity, which is that I stay. So now having this lazification idea in mind, which you can apply to any random walk and just slows it down by a factor 2, I can rewrite this theorem, which says that if you have a graph which is connected, I don't need non-bipartiteness anymore. Then if I run this half lazy random walk, I'm going to converge to the stationary distribution. And it's the same distribution because the degree of every vertex is now twice as it was before. So it's basically the same distribution. Okay, good. So we understand this. Now, the next question you can ask is that, okay, now we know that you're going to get to the stationary distribution, but how long does it take to get to the stationary distribution? So this quantity is studied under the notion of mixing time. So before saying that, I need to define a metric between two probability distributions. So let's say you have two distributions, mu and nu. You can define this metric, which is so-called the L1 distance between these two distributions, summation of I, absolute value of mu I minus mu I. Okay? So if these are exactly the same, this distance is 0. And if they're completely different, supported and disjoint part of the probability space, their distance is 2. So the closer to 0 means that the closer they are to each other. Now, let's say you're given a random walk with transition probability matrix P tilde. It's a the half lazy transition probability matrix P tilde. And the stationary pi, the mixing time, let's say the epsilon mixing time starting at V is the time it takes for a distribution started at T after time T to get to epsilon distance of the stationary distribution. So I want to find the first time such that my walker, the distribution of my walker is very close, is at distance epsilon of the stationary distribution. So you can take epsilon whatever you want for your particular applications, but typically in practice, something like epsilon about 1/4 or 1/8 would work nicely. Now, the question is, what can we say about the mixing time of a random walk? So here is a classical theorem in this field. So let's look at the eigenvalues of this transition probability matrix P tilde. Let's say these are the eigenvalues, lambda 1, lambda 2, etc. of the eigenvalue of P tilde. And say you start your random walk from V, from vertex V. Then you can prove that the mixing time is sandwiched between these two quantities, at least 1 over 1 minus lambda 2. And at most this much, log of epsilon pi V over 1 minus lambda 2. So the thing I want you to pay attention here is this quantity in the denominator, 1 minus the second eigenvalue of the transition probability matrix. This quantity is called the spectral gap. And it's a very, very important quantity. Essentially, this is the quantity which dictates how long does it take for my walk to mix, okay? The thing is, the quantity in the numerator is logarithmic. So even if epsilon is like exponentially big, or this pi is exponentially, epsilon is exponentially small, or pi is exponentially small, this is only a polynomial what I'm saying is that even if your epsilon exponentially is small, this is not the dominating factor. Usually the spectral gap is dominating factor, and we want to put a bound on that quantity, okay? So now, having this in mind, let me just show you some examples of graphs with their mixing times. So here are 4 examples of graphs with their mixing times. We have the cycle, grid, complete graph, and the generalization of the cube. It's called the hypercube. So in the cycle, the mixing time is very slow. It's n squared. And in the grid, it's also slow. It's about, sorry, there is a typo here. This should have been n. It's not n squared. It's not root n. It's n. In the grid, it's n. Whereas in the complete graph or in the hypercube, it's logarithmic in the size of the graph. So this is very important here. It says that you can, even though it says that even if you have, for example, this hypercube or the complete graph, which is huge, it could have a lot of vertices, you're going to mix in time logarithmic on the number of vertices. Before seeing all of the vertices of the graph, you will mix, okay? And this would be the sort of guiding factor throughout this talk. So what I want to study in this talk is this method called Markov chain Monte Carlo method. So what is it about? We want to design a Markov chain or some random walk to, sample from a given probability distribution, which is of my interest, okay? So the question is how to design this Markov chain and how to prove that its mixing time is good. But as I said at the beginning of the talk, the distributions that we are interested in have exponentially large support. So ideally, we would like to design Markov chains which look like hypercube or a complete graph, meaning that even though these Markov chains are over exponentially many vertices, your mixing time is only logarithmic or maybe polylogarithmic, and that will allow you to say that you will get a random sample very fast. Okay, so let me tell you about this Markov chain Monte Carlo technique. What I'm going to tell you about now is first I will tell you how to design a Markov chain that has a given distribution as it's a stationary distribution, and then I'll tell you how you can analyze this Markov chain and prove that the given distribution is indeed a stationary distribution. So let's go to the design part, and let me first remind you what a Markov chain is. So a Markov chain is very similar to what we just talked about, except that it's a random walk in a weighted directed graph. It's not on the unweighted graph, it's on the weighted directed graph. So here I'm gonna write for a Markov chain. I'm gonna write omega for the state space, and I'm gonna write P to denote the transition probability matrix, similar to what I had before, except that here I'm gonna move on directed edges, and I'm gonna say that. We have a similar theorem as what we said before, that if my transition probability matrix is half lazy and my graph is now strongly connected, then there is a unique stationary distribution. So here's a simple example. So this is a walk on a directed path. And here the point is that the edges are weighted. So each time the probability that I go to the right is twice of the probability that I go to the left. Okay. Because the edges are directed. And if you look at, try to figure out the stationary distribution, you see that it actually follows the exponential pattern. Like the probability of this guy and all the way to the right is 3 times the second one, 3 times the second one. So this is like about 3 to the minus n, 3 to the minus n minus 1, and so on. Now, the difference of these type of general Markov chains is that it is much more difficult to find the stationary distribution. You cannot just look at the degrees and say that the stationary distribution is just the degree over the summation of the degrees. But there is a special case. If you can prove an equation, then you can figure out the stationary distribution. So if you can find some function mu on the state space of your Markov chain, such that for every pair of states, mu of x times the probability of going from x to y is the same as mu of y times the probability of going from y to x, then you can say that mu is indeed a stationary distribution. So this equation is called the detailed balance condition. You cannot necessarily satisfy this equation for any Markov chain. You can satisfy it if the Markov chain is equivalent to some random walk on undirected graphs. So in other words, the Markov chain is satisfied are the same as the random walks we were studying so far. It's just that they look like directed, but they're inherently undirected. So you can build an undirected graph which does exactly the same, has exactly the same distribution. So what I want to do basically now is to give you some examples of how to design a Markov chain that has a given probability distribution. Okay, so let's go to the design part. So let's start with a simpler case. Let's say you want to design a Markov chain with a stationary distribution pi. Okay, and let's say pi is uniform. Now I'm saying by this detailed balance condition, if I'm trying to find some transition probability matrix P such that gives me uniform, it's enough that for every pair of states X and Y, P of XY is the same as P of YX. So that's all I need to do. Construct a P, that P of XY is equal to P of YX for all pair of vertices X and Y, and P is connected. It gives you a connected graph. So here is a well-defined example. Let's say you want to design a Markov chain to give a uniform distribution on spanning trees as the stationary distribution. So here are two Markov chains which give you that. Let's say here's the first one, which says that given T, given a spanning tree T, first you, like this one, given a spanning tree T, first you add a uniformly random edge which is not in the tree. For example, here, this orange edge is not in the tree, so I add it to the tree. After that, you're going to get a cycle in your tree, right? Because it was a tree, you added a new edge, you get a cycle. Now you choose a uniformly random edge from this cycle. For example, this green edge, or it could be the edge that you just added, and you delete it. Now you're going to get to a new spanning tree. Okay, so this is a Markov chain, and something you can check for yourself is that the probability that you go from this left tree to the right tree is the same as the probability to go from the right tree to the left tree. Because to go from the right tree to the left tree, you have to add the green edge and remove the orange edge. And that has exactly the same probability. So this immediately says that this Markov chain has a uniform distribution over spanning trees. There is a dual version of this Markov chain, which also gives you a uniform distribution over spanning trees, which is that given a spanning tree T, first you remove a uniformly random edge E, and then you're going to get the cut with no edges. In that cut, you're going to add a uniformly random edge from the cut to the tree. And that also has a uniform distribution over trees. Okay? So this was an example of how to design Markov chains, which has uniform distribution as their stationary distribution. Now let me tell you a more sophisticated example. Let's say you're shooting for a given distribution pi, which is not uniform. And here is a recipe to do that. It's called Glauber dynamics. So given a set S, here's what you do. You, let's say, so remember that you want to choose, to have some distribution over subsets of 2 to the n. That's what I want to think about. So you have a set S. What I'm going to do is that I'm going to choose a coordinate from 1 to n. I forget about whether this coordinate I is in my set or not. And I sort of randomize it, meaning that there are two options, whether I should be in S or I is not in S. I know that the probability that, so I know that at a stationarity, when I is in S, I get pi of S union I, and when I is not in S, I get pi of S minus I. So I would go to this state, to the S union I, with probability pi of S union I over the sum, and I go to the other one otherwise. So here is an example. Let's say you want to design a Markov chain on independent sets of a graph G with n vertices, but here you don't want to have a uniform distribution in independent sets. You want to have a distribution where the weight of every independent set is proportional to lambda to its size, to the power of its size. And lambda here is some parameter that you can choose in your problem. So for example, if you let lambda to be 1, you get a uniform distribution of independent sets. But if you make lambda bigger and bigger and make it go to infinity, this would be a distribution over maximum independent sets of a graph. So now let's follow the same thing. Given a graph G, you choose a uniformly random vertex. For example, here I choose this guy. It doesn't have to be a vertex inside my independent set, but just some vertex. I forget about whether this vertex is in or not. I just ignore that information. Now with probability lambda over 1 plus lambda, I will add it back. I will add it. And with probability 1 over 1 plus lambda, I don't add it. Where did these numbers come from? It's exactly these ratios. If you just cancel it out, you see that the probability of the probability of the left scenario, the left case, is lambda times the probability of the right one. That's why you have to go to this guy, probably lambda over 1 plus lambda, and the right one to probably 1 over 1 plus lambda. Okay, so what have we said so far? We talked about random walks, we talked about Markov chains, and I told you, given some ideal distribution, how can you design a Markov chain with that distribution as the stationary distribution? Now, that doesn't necessarily tell you that if you run this chain I just explained on independent sets, or this chain I explain on spanning trees, it will mix to a uniform distribution, it will mix to a stationary distribution fast. In fact, if you let this lambda to be very huge, this distribution will never converge to the stationary distribution polynomial time. It will take exponential time. Because if lambda is huge, this distribution is essentially distributed over the maximum independent sets of a graph. So if you can generate random samples from that distribution, you can find the maximum independent set of a graph. So it's not true that such a Markov chain always mixes in polynomial time. But let me tell you now what is true. Here are two theorems we have proven recently, and together with some other people. The first one says that, let's say you have any graph G with m edges, you start at any spanning tree T, and you run this add-remove Markov chain I just talked about, meaning that if each time you add an edge, not in the tree, and then in the cycle you remove a uniformly random edge, then this Markov chain mixes in time m log n. And if you use a data structure called link cut trees, you can implement every step in order of 1 time. That means that in order of m log n, you can generate a uniformly random spanning tree in a graph. Remember, a graph can have exponentially many spanning trees, and I'm saying that using this Markov chain allows you to sort of generate a uniformly random one very fast. Here's a second example. Here you show that for sampling independent sets, if lambda is not big enough, is less than this threshold. So this is a fundamental threshold. I'm not going to tell you about it. There are proofs that above this threshold, it is NP complete, it's NP hard to basically find a random independent set. But what we show essentially here is that below this threshold, you can find a random independent set in time n log n. Here I make an extra assumption that the graph is bounded degree. Even if the graph is not bounded degree, the running time will be slightly more. But if the graph is bounded degree at least, then the Markov chain on independent sets I just explained will generate a random independent set with probability lambda to the probability of independent set is proportional to lambda to its size in time n log n. Now, the message I want to tell you about is that these algorithms are in fact very fast. That both of them basically work in the same time as sorting. Like it takes you m log n to just sort the edges of a graph. I'm saying in the same time you can generate a random spanning tree among exponentially many options. Okay. So what do I want to do for the rest of the talk? So far, I didn't tell. This was sort of a background materials on Markov chains, random walks, mixing time, etc. What I want to tell you about is an actual research I've done over the last few years in this area. I want to tell you some of the ideas to prove this theorem. Okay, I don't get you exactly this theorem, but I'll get you something close. So let's begin. So as I said, the main challenge is that now that we have a Markov chain, we want to bound its mixing time, or in other words, we want to bound the spectral gap of the transition probability matrix associated to my Markov chain. And the question is, how do we do that? I should say that this field of Markov chain and Monte Carlo technique, it's been around for decades, for 3-4 decades. A lot of techniques you can use to study a Markov chain and study its mixing time. I'm not going to tell you about all of them. What I want to tell you about is this new technique we have been using to analyze these Markov chains. It's based on a mathematical object called high dimensional expanders. So let's begin. What I'm going to tell you is that first I will tell you what a simplicial complex is. And I'll tell you about high dimensional walks and links of simplicial complexes. And then I'll use these notions to study mixing time of the Markov chain and spanning tree. So let's start. Let's start with what a simplicial complex is. So let's say you have a ground set E of elements. A simplicial complex is a subset of, is a basically family of subsets of this ground set, where the main property is that it's downward closed, meaning that if you have a set in your family, you have all of its subsets. The sets in my family are called faces. So anything in my family is called a face sets. So let me show you an example. So you can study a simplicial complex by its geometric view. So let's say I have 4 vertices in my simplicial complex, 1, 2, 3, 4. In the right, I'm drawing so-called a diagram of a simplicial complex. So I must have the empty set. I have the singleton sets, 1, 2, 3, 4. Let's say I have these edges that I've shown. So far a simplicial complex could look like just a graph. I have an edge between these pair of vertices. Analogously, I have changed my diagram. I added a set for every edge, like a set 1, 2 for the edge 1, 2, and so on. But I have one more layer. Let's say I have sets also of size 3, meaning that I have so-called triangles. I have this triangle 1, 2, 4, 1, 2, 3, 2, 3, 4, and 1, 3, 4. So I have 4 triangles. Those are also I added also those to my sets. So I get this diagram of my simplicial complex. And here, one thing I want you to note is that the edges between these different layers of diagram are drawn when a set is a subset of something above. Like for example, I connected 1, 2 to 1, 2, 4 because 1, 2 is a subset of 1, 2, 4. Okay. So I have a simplicial complex. I have its diagram, and I want to study this. Let me show you one example to just think that why is this related to spanning trees or independent sets I was talking about. I'm just focusing on the spanning trees, but similar stories can be said about independent sets. So let's say you have a spanning tree. You want to study spanning trees of this graph that I have here. It has 4 edges, A, B, C, and D. So the graph has 3 spanning trees that I've shown. And you can build the simplicial complex or build the diagram here. Basically, for every forest of your graph will be a set in my simplicial complex. And I have these edges when a forest, like this forest has an edge to this tree because it has 1 edge less than that. So I get exactly the diagram I was talking about. So now, what I want to study are these simplicial complexes, and I want to use them to analyze the Markov chain on the spanning trees. Okay, so let me just define some notation which will be useful. So if you fix an integer k, I'm going to write x of k to denote faces of my simplicial complex that have size k. This would be basically the level k of this diagram I've been drawing. Here's another notation. Let's say you fix some distribution on top faces of my simplicial complex. But in our particular case, you fix some distribution on spanning trees, pi n minus 1. This distribution induces a distribution on faces 1 layer lower, where the way I'm going to do it is that given a spanning tree, I'm going to remove one of its edges uniformly at random, and then that will give me a forest of size 1 less. So if you fix a specific forest with say n minus 2 edges, the probability of that forest will be the summation of all the spanning trees that contain this guy. The probability of those trees by n minus 1. That's the probability that I remove a specific edge to get to this forest. I'll show you one example to see how this is done actually. And you can repeat this to define a distribution on every layer of the simplicial complex. So here is an example. Let's say, go back to this graph. Let's say you're interested in a uniform distribution on spanning trees. Now let's see what distribution does this impose on trees, on forest in the next layer. So I'm saying this is a distribution. Where does this 2/2/9 come from? To come here, either I start from this tree, which has probability 1/3, and I delete the edge, the red edge, which has probability 1/3 because there are 3 edges. So that gives me 1/9 probability to come here. Where I come from this guy, which is again has probability 1/3, I have to delete the orange edge, which has probability 1/3. So I get another 1/9. So 1/9 plus 1/9 is 2/9, and so on. Similarly, I get a distribution on forests of size 1. The probability of this guy, for example, is 1/3 because either I come from this set, which has probability 2/9, and I delete the blue edge, which has probability 1/2, or I come from this edge, this set, probably 2 9. I delete the red edge, again 1/2, 2 9 and 1/2. Where I come from here, 2 9s times 1/2, so I get 1/10. And at the very bottom, I have the empty set, which has probability 1. So I have a distribution on every layer of this simplicial complex. Okay, sounds well. So now I'm ready to define this so-called random walk on this on 2 consecutive layers of the simplicial complex. This was introduced by Kaufman and Moss a few years ago. So let me show you how it works. So let's say you start from, fix this distribution on top. Let's say I have uniform distribution on spanning trees here. I start from some guy. Let's say I start from here. Then I add a uniformly random edge. I see I have these 3 options to delete. So maybe I delete the blue edge. So I get to this forest. Now, I came down so far. Now I want to go back up. How do I go back up? I see which trees have my specific forest. These 2 trees have them. So I go to one of them proportional to its weight. So the weight of these 2 are the same. Both of them has 1 pair probability. So I just go to one of them uniformly at random. So maybe I go to this guy. Again, I'm going to come down. There are 3 options to delete my edges. Maybe this time I delete the red edge again. I go back up. There are two trees which have my forest. The probabilities are the same, so I choose one of them uniformly at random. I go back up and so on. So if you think about it, this random walk, this down-up walk I just explained is exactly the remove add Markov chain on the spanning tree. Basically, all I'm doing is that each time I have a spanning tree, I delete a uniformly random edge, then I get a cut, and in that cut, I add a uniformly random edge from the cut. But that's exactly the remove add Markov chain I talked to you about. So the main thing we need to figure out, so I'm going to use this notation P down up 3, or in general P down up n-1, to denote this Markov chain, the remove add Markov chain on spanning trees. And the main thing I have to figure out is that what is the second eigenvalue of the transition probability matrix of this random walk, this down up walk. And as we will see, I will show you later that this second eigenvalue of this matrix is at most 1 minus 1 over n minus 1. So it's 1 over n minus 1 away from 1, and that gives you a spectral gap 1 over n minus 1. Okay, but let's see how we can prove this. But that's the main question I want to study. So before we go further, I want to just tell you 2 observations, 2 facts. Basically, one is that this walk I just defined, where it's a down-up walk, there's a dual walk, which is the up-down walk, meaning that you can just do the same thing, start from a forest of size 2, first go up and then come down. I'm going to use this notation, maybe P up down of k minus 1, where you start from a forest of size k minus 1, you go up and then you come back. Now, the thing is, this operation I just defined, you can define it for any graph, any simplicial complex, and any k. You can come down and then you can go back up. So these matrices are well defined. And here is a cool fact that these 2 matrices, so look at P down up of k and P up down of k minus 1. I'm saying they have the same eigenvalues, same non-zero eigenvalues. Basically, if you look at them, P down up of k starts from a level k in this graph, comes down and then go back up. P up down of k minus 1, it starts from the bottom layer of this bipartite graph, goes up and then comes down. So they're basically, both of them are taking 2 steps on this bipartite graph, each starting from different sides. The reason they have the same non-zero eigenvalues follows from a well-known fact in linear algebra, which is that if you have 2 matrices A and B, the non-zero eigenvalues of A times B is the same as the non-zero eigenvalues of B times A. Okay, this is a well-known fact in linear algebra, and from this you can say that basically a down-up walk at level k has the same non-zero eigenvalues as the up-down walk of level k. Okay, so having this in mind, I want to now tell you how to bound the second eigenvalue of a down-up walk at level n minus 1. I need one more definition, a definition of links and the corresponding matrices. So let's say you have this simplicial complex X, and let's fix a face S. I want to study the link at level, the link of the face S. So what is this link? Is the set of all sets T such that T union S is a face of my simplicial complex, and T is disjoint from S. So here is a simple example. Remember the simplicial complex I was telling you about. I want to look at the face of the set 3. I'm saying the face of the set 3, I have vertices 2, 1, and 4 because 2, 3, 1, 3, and 3, 4 are edges of my simplicial complex. I also have edges here. Remember, I had a triangle 1, 2, 3 that gives me an edge 1, 2. I had a triangle 1, 3, 4 that gives me the edge 1, 4, and I had a triangle 2, 3, 4 that gives me the edge 2, 4. The triangle 1, 2, 4 doesn't give me anything because it doesn't have the it doesn't have 3. It also defines a distribution. Remember, I was looking at the uniform distribution over these triangles. Only 3 of them remain, but because the distribution was uniform, it remains uniform here. If it was not uniform, this distribution here, it would be proportional to the weight of the corresponding triangles in the original complex. Okay, so if you have a complex with distributions associated to some faces, when you look at when you fix some face S, you're going to get another complex, which is another simplicial complex, which is the link at S, X of S, where and then the probability distributions correspondingly extend to this new link. So let me show you one more example and then tell you about sort of one skeleton and local random walk. So let's look at, again, our spanning tree example. Let's say I want to look at the link of edge A. Okay, so what do I have in edge A? I have 3 edges. Sorry. I have 3 edges. I have the edges BC. A comes with B and C, with C and D, and with B and D. So my simplicial complex would look like this. And because I had a uniform distribution over spanning trees, I would have a uniform distribution over these 3 edges. So I would get this graph. And you can associate to this graph the corresponding matrix, the corresponding transition probability matrix of a simple random walk. And because all edges have the same weight, this is exactly the corresponding transition probability matrix. For example, if I start at B, I go to C or D uniformly at random. So I would put half and half here. So this is a transition probability matrix, PA, for the link at A. Okay. Now, let's do one more example. Let's look at the link of the empty set. The link of the empty set, this is exactly the whole simplicial complex, but I want to build a graph out of it. How do I build a graph? I basically ignore faces of dimension 3 or more. I just look at faces of dimension 1 or 2. So this object will give me a so-called one skeleton. I just look at faces of dimension 1 and 2. I put a vertex for every face of dimension 1. I put an edge for every face of dimension 2. So here I have, for the empty set, I have 4 faces of dimension, 4 faces of size 1, A, B, C, and D, and I have 6 faces of size 2, A, B, B, C, A, D, B, D, A, C, and C, D, and these are exactly all the edges. I look at the distribution here. I have 2, 9, 1, 9, so on. I just put those weights on these edges. And now I can, again, write the transition probability matrix of a simple random walk on this graph. For example, if I start at A, I have 3 options to go on, these purple edges, right? Because all of them have the same weight. For A, I put 1/3, 1/3, 1/3. Whereas for B, there are 3 options and they don't have the same weight. BA has weight 2/9, whereas those others have weight have the same weight. So I put half here and 1/4, 1/4. So I get this matrix. And what I've shown below here is that I've written the second eigenvalue of this so-called local random walk matrix. So again, what I've done here is that I fixed the link A or the empty set. I look at the so-called one skeleton. I write the transition probability matrix of the simple random walk, and this I've written to you here the second eigenvalue of the local random walk, or the transition probability matrix of the one skeleton of this link. Okay. Now let's go back to what we were trying to show. We were interested to bound the second eigenvalue of the up-down walk at level n-1, of the up-down walk over a spanning tree. Here's the thing we're going to see, that we're going to see that if all of the faces that have exactly n-3 edges have very, very small eigenvalue, then in their local random walk, then the second eigenvalue of the down-up walk is small. So this fact is so-called the local to global fact. And it's a very fundamental property of simplicial complexes, and that's exactly what allows us to analyze the Markov chain on spanning trees and similar other examples. So we will study the random walks, the local random walks on these links, and then analyzing the eigenvalues of this local random walk, it allows us to analyze the eigenvalues of this big giant matrix on all the spanning trees of my graph. So let me be more precise. So it turns out that you can prove a lemma. I'm not going to tell you how to prove it, which relates eigenvalues, the second eigenvalue of the up-down walk at level k, and the second eigenvalue of the down-up walk at level k, modulo some loss which comes from the local random walks of links of sets of size k minus 1. So think about it like this. Remember, I said that a down-up walk at level k have the same non-zero eigenvalues as the up-down walk at level k minus 1. Now, once you put this together, this lemma allows you to relate second eigenvalue of the up-down walk at level k to second eigenvalue of the up-down walk at level k minus 1. And then you can induct, okay? So this is, I'm not going to tell you how to prove this. This may look a bit fishy, but this is sort of the main mathy part of the proof. I'll just tell you the main consequence. The main consequence is this theorem. Let's say you have a simplicial complex X, and I'll say that it's alpha 0, alpha 1 up to alpha n minus 3 local spectral expander. If for every phase S, the second eigenvalue of the local random walk of the link at S is at most alpha of the size of S. So empty set has second eigenvalue alpha 0, sets of size 1, the local random walk has second eigenvalue alpha 1, and so on. Then you can bound the second eigenvalue of the up-down walk at very high, at the very top, with the up-down walk of the walk on spanning trees by this much, by 1 minus 1 over n minus 1 times the product of these 1 minus alpha. Like the way, okay, like there's some intuitive way to think about these things. The thing is that this is basically saying that if these alpha i's are bounded away from 1, then these local random walks on these links they have a very good mixing time. They have a very fast mixing time. So this lemma and this theorem says that somehow you can decompose this up-down walk on all of the spanning trees of your graph as some averaging of these local little random walks. So if all those little random walks are fast mixing, the random walk on this giant random walk on all the spanning trees is also fast mixing. Okay? So that's the way to think about it. Now, how did we prove what we wanted to prove? What we show is that for our specific example, if you have any graph G, all of these alpha i's are 0, meaning that you can put 0 here, or all of the second eigenvalues of the local random walk matrices are less than or equal to 0. So I can put 0 here, and if you just simplify this, you get that the second eigenvalue of the down-up walk is at most 1 minus 1 over n minus 1. That says that the spectral gap is 1 over n minus 1, and that says that the mixing time of the Markov chain, of the remove add Markov chain on spanning trees is at most n times log of the number of spanning trees. This doesn't give you m log n, I was saying at the beginning of the talk, but gives you a polynomial bound, because you only have at most n to the n many spanning trees, so this already gives you a maybe n squared or n squared log n mixing time. So I just want to tell you for one minute, how did we bound these alpha i's by 0? There is another sort of theorem in this theory of Markov chains, which essentially say the following. It says that if you can prove that the alphas at the very top are less than or equal to 0, then all of the alphas are less than or equal to 0 as well. It's something more general, but let me not get into it. So in other words, it says that if you look at faces of size n minus 3, if all of the local random walks there are small or less than 0, then all of the local random walks of every lower face is 0 as well. So you just need to analyze the top. If the top is good, everything else is good. So now to prove this theorem, I wanted to prove all of its alpha i's are 0. I just need to prove that the second eigenvalue of the local random walk for forests of size n-3 is less than or equal to 0. So let's just prove that. So let's fix a forest S with n-3 edges. I want to study the local random walk of S. So I fix this forest S. Let's contract the edges of this forest. The remaining graph has only three more vertices. And it has two options. Either it looks like this, it looks like a triangle, or it looks like a wedge I have in the right. You can write down the second eigenvalue of the local random walk matrix for each of these graphs. Here you get the second eigenvalue -0.5. In the right, you get the second eigenvalue 0. And that's it. There are some other cases. The graph, after contracting this forest, you may have some parallel edges or loops. But the thing is that doesn't change eigenvalues much, and you still get the same map. So so this immediately says that I can let alpha of n-3 to be 0, and then by this theorem I just explained, if alpha of n-3 is less than or equal to 0, all alpha i's are less than or equal to 0, and that's all I need to prove. So to recap, what I talked about, I sort of gave you ideas of this proof, that not the add remove Markov chain, but the remove add Markov chain on the spanning trees. When you remove an edge and then add another edge in the cut, mixes in time n squared log n. That's what I talked about. You can follow similar type of ideas to prove this is slightly faster running time, that the add remove Markov chain, when you first add an edge, and then in the cycle that you get, you remove a uniformly random edge, mixes in time m log n. As well, another thing is that this method I talked to you about, using the simplest shell complexes, is in fact much more general. You can use it to say that a similar Markov chain basically generates a uniformly random base of any given matroid. If you don't know what the matroid is, for example, think about a set of vectors and say you want to generate a uniformly random set of linearly independent vectors of size k. You can use Markov chains similar to this to generate those. Okay, let me conclude the talk. So this field of Markov chain and mixing time and the Monte Carlo method, it's a very active area of research in sort of theoretical computer science. There's a lot of activities, there's a lot of beautiful math, and a lot of nice and simple algorithms to implement. I want to conclude the talk with 3 open problems to sort of motivate you to work in this field in future, maybe. The first one is a sampling problem, sampling of a random coloring problem. So here you're given a graph G, and let's say it has max degree delta. You know that by a greedy algorithm, you can color such a graph with delta plus 1 colors. Now say I give you more colors. I give you delta plus 2 colors or delta plus 100 colors. Can you find a uniformly random coloring of a graph, of vertices of the graph, uniform random proper coloring of the vertices of a graph using delta plus 100 many colors? This is one of the biggest open problem in this field, and we have no idea how to prove. Here is another one. You're given a graph G, you want to sample a uniformly random perfect matching in that graph. We know how to solve this if the given graph is bipartite, but it has been a very long-standing open problem how to do this for non-bipartite graphs. And the last one is to sample so-called rainbow spanning tree. So here you're given a graph G, you color its edges with n-1 different colors. A rainbow spanning tree is a tree where all of the edges have different colors. And the problem is that given a graph, can you sample a uniformly random rainbow spanning tree? That's another open problem. We have no idea how to solve in this field. So that's it. I hope you like this talk and you will work on Markov chain Monte Carlo method in future. Thanks. I'll stop here.